Christopher G. Brinton is an assistant professor in the School of Electrical and Computer Engineering at Purdue University. He is a co-founder of Zoomy Inc., a big data startup company that has provided learning optimization to more than 1 million users worldwide and holds a US patent in machine learning for individualized learning. His book, The Power of Networks, 6 Principles That Connect Our Lives, and associated massive open online courses, which is in short called as MOOCs, have reached over 4 lakh students to date. So Chris, it is great to have you talk at the event. So thank you for accepting the invite. I invite you to go ahead with your talk.
Sure. Thank you so much. Thank you for the introduction. Let me go ahead and share my screen if that's okay. It says the host disabled participant screen sharing. I think maybe somebody has to make me a co-host.
Yeah, Chris, go ahead now.
Here we go. All right. So let me, great. Okay, can you see my slides okay?
Yes, Chris, yeah.
All right, great. So hi, everybody. Thank you. Again, my name is Chris Brinton. I am an assistant professor in ECE at Purdue University. And so I'm going to talk to you about some different aspects of FOG, FOG communications, and particularly more on the machine learning side of it. You know, so just to give you a little sense of what's been going on in this space, you know, and some of what researchers, including myself, have been doing. So since I joined Purdue in fall of 2019, and before that, appreciate the introduction. I was in industry for a little while at a company that we co-founded. Funny, when I joined the talk, well, we were actually mentioning one of the biggest enablers, or one of the technologies that's being enabled by future 5G technologies is going to be distance learning. And it's funny because that was one of the things that I focused on in my past life, is really doing machine learning for education. And then I came more over onto the communication side of it since I've been at Purdue, but I guess 5G is kind of integrating everything at this point. So it's very cool to see that people are talking about that too. So since I've been at Purdue, I've been focused particularly on machine learning and communication networks. And so I'm going to talk to you a little bit about that. All right, so machine learning and networks, right? These two words, two fields that traditionally have been separated, but now today more and more are becoming unified, right? There are growing applications at the intersection point between these two areas, right? And this is really motivated by the proliferation of 3 factors, at least 3 factors, maybe more. One is the number of intelligent devices that are out there today. So you can see on the right side here, I'm just using Cisco's Visual Network Index that they publish once a year. You can see how devices are growing, very fast scale. Also, the amount of data, right, that's being generated by these devices at the edge, by end users, and even with devices that aren't being managed by users anymore, machines, drones, and smart cars, and these kinds of devices as well. And the third is the need for real-time intelligence, right? There are a lot of applications, you know, whether they range from medical or biomedical applications, right, to doing health monitoring, to navigation of smart autonomous vehicles that really require a lot of decision-making to be done in real time, right? And so that's one of the other motivating factors for bringing machine learning into this community in the networking space. So there's 2 different aspects of this. I like to divide this into. You can think of machine learning for networks, and you can think of machine learning by networks, and that gives us machine learning and networks. It's kind of this bidirectional relationship. So machine learning for networks is trying to use machine learning to really optimize the efficiency of networks and how they operate. Optimize how devices are communicating with one another. So reinforcement learning in particular has been a very big aspect of trying to do this sort of optimization, trying to revisit how certain protocols have been built in the past based upon data now, and to see if we can optimize them more in real time. and really optimize the network operating efficiency. There's also machine learning by networks, right? Because there are machine learning tasks that really have nothing to do with networks, but that we need to have done by networks by virtue of how the data is being collected and managed and operated, right? Like you can think of, for example, recommendation systems, personalization of content, right? Fundamentally, we are the end users with our devices. We're the ones collecting data, processing that data. And so we need to figure out a way to be able to do machine learning with this kind of data over the networks that are collecting the data, right? So there's really these two different aspects. And for this talk, more specifically, I'm going to be actually on the second question, this machine learning by networks. How do we have networks support the ever increasing demands for machine learning applications? Okay, so traditionally, machine learning has been managed in a very centralized manner. Okay, so model training has traditionally been a centralized process, right? And in a centralized model training procedure, the way that would work is that devices or whatever nodes are actually collecting the data. They could be devices, it could be something else. I'm calling them devices here. They send their data to a central server or some central processing entity, typically a server in a data center somewhere, okay? Then the server is going to actually train the model, right? Do the training. Usually those are through gradient methods. And for those of you who are familiar with gradient methods, it's really applying some really basic principles of calculus actually to try to minimize an error metric. To say building the best model for the data set that's possible by looking at the gradients applied to the data. And then third is the model or the result, not necessarily the model, would then be passed back from the server to the devices, right? And so this is really based upon this putting the intelligence in the core of the network in the data center. That's where the machine learning is happening. It's where the decision making is being done, right? This is how machine learning has been thought of traditionally, right? Before we got into all of the different networking aspects of it. So I see that there are some hands raised and so forth. Am I supposed to call on people? I just wanted, what is the suggested format?
Christopher, you finish your talk and then I'll post some questions.
Okay, sounds good. All right, thank you. Great. So there are issues though with centralized machine learning today. And they get brought up in several different ways, but it really has to do with the fact that a lot of researchers in the machine learning community haven't really been considering networking and all the different considerations that come along with networks. Until now, this is becoming very important to do so. So there's three main groups of issues. There are even more than this, but these are just three that we'll focus on today. Not so much the third one, but the first is resource utilization, right? So your edge devices, devices are where the data is being collected in the first place, right? So the devices have to actually upload this data. And those can be very large volumes of data because we have literally, not hyperbole, literally an exponentially increasing amount of data being generated at the edge today, right? So the devices may not be able to handle that much uploading all the way, to a server, right? If you're far away from a cell tower, it can drain battery and so forth. Related to this are latency restrictions, right? Because many applications today, I mentioned some of them before, self-driving cars, navigation, health, bioinformatics, these need fast response times, right? So this centralized machine learning aspect of having the data originating on the device, sending it all the way to the server, having the server do all the processing across all of the data, and then distributing that result back out the devices, that actually can incur a lot of latency by the time it's all said and done. And so that is another restriction with centralized training. And third is more fundamentally just privacy sensitivity, right? Some users today, especially when we see different issues with how, say, Facebook handles our data. There's been a couple of news items on that, certainly in the past few years. users may not want to share their data at all, right? You may not be comfortable with the fact that your data is going to a data center because you may think that it could be compromised for whatever reason when it's there, right? So with these three issues, these are three big networking consideration issues with centralized machine learning today. And what that has done really is it's motivated a migration from centralized machine learning to distributed machine learning, where in distributed machine learning, there's a lot of different ways that you can define that. But in the simplest way, we have more local processing of data and local model building between local devices. And they may be shared at a longer time period with more centralized parameter server, right? But this sharing with the central entity is not happening super frequently. So all of the really latency intensive type learning is happening right at the edge here, right? So the simplest way to think about this when you think about distributed learning is that, I'm just going to start grouping devices, local devices together. If we're talking about, cell phones communicating with the base station, it could be all users that are in a given cell, for example. If even more granular than that, you can talk about users that are sharing the same access point in the Wi-Fi network, right? So this is the idea of going to distributed learning. So now, the most recently popularized solution for distributed machine learning, there are a lot of them, is what's called federated learning. This is made popular by Google over the past 5, 6, or 7 years. Okay, so in the federated learning paradigm, the way that federated learning works is that we don't have any data actually moving away from devices at all. All the data stays entirely local at devices. We have each device collecting their own local data sets. They all train their models based upon those local data sets, take the trained models, and then pass the trained models back to the server. Okay, so the server gets the models, not the data anymore. And then the server will do what's called an aggregation, where it will aggregate those local models into a global model. And that aggregation can literally be an averaging of those local models. Typically, it's actually a weighted averaging because some devices will process more data than others. And when a device processes more data, we tend to view that device's model as being more reliable. So we factor it in higher into the average. Then once that average is done, or the aggregation is done, the server synchronizes the devices to start a new period of local learning again, right? So you have this repeated process between local model training and global model synchronization. Okay. So now, federated learning has some challenges when we start to try to look at this in fog environments too. Okay, so distributed learning doesn't necessarily mean it's applicable in a networking context. There's some work that we still have to do, and that's being done today. And that's really, if there's one thing I want you to take away from this talk, it would be that there are certain enhancements, there are modifications really in a large way that needs to be made to this paradigm of federated learning to have it work at a large scale in fog computing. Right, so fog computing, as most of you probably know, this is all about the cloud to things continuum, right? At least one definition of it. There's a lot of people that have a lot of different definitions for fog. Today, the one we're going to stick with for the purpose of this talk is the cloud to things continuum. All right, so we have from the cloud, we have some more, through the backhaul and so forth. We have to different devices, different access points, base stations. You can think of a whole hierarchy of nodes between the cloud and then the Internet of Things. And the idea is that we want to be able to distribute and manage computation much more efficiently, right? So what are the limitations then that federated learning poses in this type of an environment, right? Because machine learning is really, as I've motivated in the first, several slides of this talk, machine learning is one of the key technologies really that we have to be thinking about deploying. It's one of the drivers of 5G and beyond wireless communications and so forth, right? So why can't we just use federated learning over a fog network to do that? Well, there's three reasons really, fundamentally. One, device communication and computation capabilities are not homogeneous. So in the federated learning paradigm, we are assuming implicitly that each device is roughly homogeneous in terms of the amount of data it can process, the quality of its local data set, in terms of how representative it is of the whole global data set, and further, that they each have a good connectivity with the central server, really at all times. That's not going to be true, right? These devices in the Internet of Things can vary, from my smartphone to a drone, something else, all different types of communication and computation capabilities, right? So they're certainly heterogeneous. Second, the network is not going to be connected in what's called a star topology, right? A star topology in federated learning, we're really assuming that this central entity is directly connected to each of these nodes that's doing the processing in a star topology. That's not always going to be the case. Some devices may not be connected to the central server at all. There may be multiple layers in between the devices and the central server, right? And third is that the device availability is going to vary over time, right? Devices have different tasks that they need to be doing besides just learning some personalization model that they need to be doing. And so as that availability varies, that in turn plays into actually the first point about communication computation capabilities being heterogeneous, but there's a temporal aspect to that. Okay, so in the last 2 years, at a particular conference called Infocom, which some of you might be familiar with, any of you more on the academic side, we've been proposing some certain variants really on federated learning that can help to address some of these concerns. So in 2020, last year, one of the things that we looked at was what's called federated offloading. So really combining this federated learning idea with offloading, data offloading between devices, right? So rather than having this restriction, that data cannot pass between nodes at all or pass from a node to a central server at all, what if we allow it in very local, in local topologies, right? Local device to device communications, right? Because D2D is being enabled much more frequently today in 5G and beyond, as well as in IoT. There are protocols coming out, particularly for how drones communicate, how smart cars can communicate directly with one another. So can we leverage device-to-device communications really to allow resource-constrained nodes to offload to more resource-abundant nodes, right? Those that can process more in a given time period, particularly to get over problems having to do with stragglers and node stragglers in the network that may really hurt processing time and so forth. So we looked at that problem. And then more recently, we looked at sampling problem, which is another way, but rather than really looking in the offloading case, we're addressing the computation heterogeneity. In the sampling case, we're actually addressing really the communication heterogeneity, right? And the fact that the devices may not at every given time have a very good connection to the main server, right? So how can we actually sample the devices over time such that we could get a good representation of what all the devices have learned, right? So can we come up with really some good type of sampling procedure? And you get really good gains by doing that, right? Because if you can sample just 10% of the nodes, that's a reduction, by an order of magnitude, right, on the amount of communication that you need to have between the devices and the server at a given time. Okay, so I am already running a bit short on time. So I had put together one specific research question that we had gone into, but I'm just in the interest of trying to stay a bit higher level, I'm going to go through this somewhat quicker. I really wanted to give you a flavor of some of the work really that's being done today on looking at how we distribute model learning across fog network topologies. Like if you consider having varying battery levels of AR and VR enabled devices, for example, trying to communicate with one another, or varying channel conditions for internet connected vehicles, right? We've recently considered this problem. And so we put together, our system model for a fog computing network, considering a time varying network and different nodes that are active at different times, right? So certain devices are collecting data versus processing data. It's a big distinction, particularly in an offloading setting. Links also have costs and they have capacity associated with them. These, even though we represent them as numbers, these are very complex objects, right? Because the costs and the capacities really depend on the channel conditions, right? That gets down into how are the devices able to communicate with one another? What's the protocol that's being used? If device I wants to send data to device J, what does that protocol look like? How much does it cost? How do we weigh that versus how much it costs to do processing and for each given data point? In our machine learning model, usually we look at, we represent a given machine learning model. Really, what it all comes down to is just a vector of parameters. It's just a big parameter vector, W. It's usually how we look at model parameter vectors. The model could be anything from a deep neural network to a logistic regression model, right? Doesn't matter. They're all going to have a set of parameters and a loss function associated with them. The loss function is measuring the goodness of fit of the model to the data set. And so then we want to build a data movement optimization model. And so this is really where, I'm not going to go into the details here, but this is where you see really the kind of network optimization type research that's been done traditionally intersect with the machine learning. So we have an objective function, which really weighs three different types of costs, two different large categories of those. Networking costs of processing and transmitting, and then error costs of the machine learning model, right? Intuitively, as the transmission costs and the processing costs go up, the error costs should be able to go down. Because if I'm processing more data, my model should get better. And vice versa. If I process less data, my model should not be as good. But that also depends upon the quality of the data, right? And so there are a lot of factors that need to be taken into consideration there as well. And so we've run some evaluations on Raspberry Pi dataset testbeds that we've constructed. And essentially what we've been able to show is very nice reductions in the amount of cost that the network needs to incur in terms of its resource utilization, relative to standard federated learning, which is not network aware. So if I had to draw your attention to one number, it would be, this is in the case where we're just doing standard federated learning, we can get accuracies of about 82, 83%, and costs of unit cost sense and versus the amount of data processing on the order of 0.4 to 8. And then in the network aware case, we're able to roughly keep the accuracy the same, even increase it in some cases, but we don't necessarily expect the accuracy to increase, but drop the costs by about 50%. So very promising results that we've been able to get. We've looked at some other factors as well. And so there's a lot of open research problems in this direction, really looking at what we term fog learning. It's the intersection between fog computing and federated learning, or fog computing and machine learning. So there's a couple of interesting open directions that really need to be investigated to get us to the point of having fog learning. One is, rather than assuming that we have a server in the first place to do any sort of model aggregation or anything like that, can we do the aggregations more locally? Can we do aggregations via consensus between devices? And what does that look like in a fully distributed solution? Also, what are the relationships between the topology of the network and the accuracy of the models, right? So how does the topology that we have affect the accuracy of the model, and how does the desired accuracy in turn affect what topology we need to build? Third one, integrating wireless channel modeling factors, and 5G being huge here, right? What do the 5G protocols look like in this realm? How do we integrate them together with fog learning? And finally is really a cross-layer system design, right? A lot of what I've talked about here is really more at the application and the network layer, but really drilling down lower layer into even physical layer considerations. So there's just, a lot of pretty interesting open problems here. And with that, I'll just thank you all so much for allowing me to do this, and for having me. I'd like to thank the organizers, thank the organizing community, and also thanks Russell very much for inviting me here to give this talk. Also need to thank all of my students at Purdue and my postdoc, and then my faculty colleagues that work together to do all this work. So with that, happy to take any questions.
Thanks a lot, Chris. It was a great talk, especially your last slide. A few points. I think people
this one, the thank you slide, not the thank you slide. This one.
So the last slide was really good, because people who would want to work on these research problems, it's a good pointer. Yeah, great. The second, I especially personally, I like the second point. I mean, that's a very good idea. I think it's great to explore that. Yeah.
If you want to, I didn't want to make it as like a plug for my own research necessarily, but we have a very extensive paper on that second point. I'd be more than happy to share.
So that will be a good pointer for people to use. Yeah.
Okay.
Chris, there are a couple of questions. I'll run through them quickly. How do we choose the model or the architecture to be used in individual devices in distributed machine learning?
How do we choose the model architecture? Well, it's interesting. A lot of cases, we assume that it's going to be the same model architecture that's used in any device. So we assume that we have a model that we want to learn, a global model we want to learn. So if that's like say it's a fully connected neural network, right? Then each device individually gets instantiated with that fully connected neural network, but their own version of it. And they update their model parameters locally. There is a more recent line of work looking at actually model parallelism, where you could actually take the global model, like a fully connected neural network, you can have literally millions of model parameters, and divide it down, right? Can I have one node do 1,000, another node do another 1,000, and so forth.
Okay, Chris, there's the next question. It's quite interesting. How accurate is the data at the edge devices when using federated learning locally?
It's really depends on a lot of factors. It depends on the quality of the device's local data set, right? Some devices collect higher fidelity data than others, right? Think of a device that has a much better camera than another one, if we're doing an image recognition task. It also depends on how frequently we actually aggregate the local model parameters, right? So the devices are doing their local training, and the more iterations they process, right, we expect their local models to then get better. So there's an interesting trade-off between how frequently we do the aggregations and how good those local models actually are when we do the aggregations, and the time that it takes. to learn the model. So it really depends on, a whole lot of factors there.
Thank you, Chris. So
I have a question.
yeah, Swami, please go ahead. Quick. Yeah.
Hi, Christopher. Right. You're comparing centralized learning and federated learning and network aware learning, right? So what exactly you meant there by network aware learning? Like, is it the topology is known at the central level, or like what exactly?
It's really good. So in this case, centralized is just everything up on data center. Federated is the standard star topology, federated learning. Network aware is where we're enabling the offloading between the devices. So the devices are still doing federated learning locally, but they can actually share data with
I learned to D2D communication. That's what.
Yeah, D2D communications. And through this optimization problem, solving this.
Okay. Yeah, I got it.
So
Thank you.
Christopher, for the problems you were looking at, if you were to do a comparison, if I do image recognition, I know how many pixels I have, I know how many colors I have. What have been the estimates of the spaces that you're looking at? Because to some extent, you have to have enough data that subtends the space you're interested in.
Definitely.
And the major problem I find in this class of investigations is most of the people don't even estimate the size of the space. So when you look at things like the DARPA Grand Challenge, what they discovered is the size of the space was 10 to the 100th power. You don't have enough data to deal with that, okay? So how do you reduce the size of the problem so it's actually tractable, okay? And I find very few people actually address that.
Yeah, it's definitely definitely a very important problem, especially when we're talking about the devices having to, themselves be keeping track of the space, right? And collect the data at the size of the space of the problem.
Yep.
I've focused more on the network. I haven't really, the machine learning problems that I've specifically delved into are actually more on the education side, like machine learning for education. Those are pretty high dimensional because we're trying to actually model like a human learning process. That gets
GPT-3, takes 1 point, the size of that is just enormous, right?
It is.
Okay.
It's a really good point. Yeah. Thank you.
Thank you, Chris. It's really a great talk. Several pointers. I think many would have enjoyed your talk, Chris. Thanks a lot for agreeing to speak. Okay, and thanks a lot.
You're very welcome. And Adam, I remember you from the days when I was in the Edge lab.
Okay.
One of Mung's students. So
sorry for asking awful questions.
No, it was great. No, really appreciate the question. Thank you.
Yeah.